So let's use this example question here as an introduction to counting problems. So we're told 8 athletes take part in a 400-meter race, and then we're asked in how many different ways can the first 3 places be arranged. So let's think, how many different athletes can possibly place first? Well, any of them. There are 8 of them that can possibly take the first place, so there are 8 different ways in which we can arrange first place. But now let's think about second place. Out of all 8 athletes, only 7 of them can then possibly place second. And then for third place, you see the same thing, times 6. Only 6 of them will then possibly be able to place third. And so we can see there are 8 times 7 times 6, and you can put that into your calculator and you'll work that out to be 336. But there are 336 different ways in which the first 3 places can be arranged. And if this looks a little bit like it has the skeleton of a factorial, you'd be dead right, We use factorials in order to make these counting problems a little bit easier. So now let's move on to another example so you can sort of see how this is working in the background when we deal with these counting problems. So here's the next example. In how many ways can 7 boys of different ages be seated on a bench if A, firstly, the oldest boy sits next to the youngest boy? So oldest boy must sit next to youngest boy. So oldest next to youngest. So how do we go about answering this? Well, let's think about this for a second. Surely if the oldest boy sits next to the youngest boy, we can sort of treat them as a single object that can move around together. So essentially we've just got 6 different objects that we're arranging in a bunch of different ways. And so we can see that there's just going to be 6 factorial different ways in which we can arrange these 6 objects. But now let's think about this. For every arrangement where the boys are sitting, where the oldest and the youngest boys are sitting together, surely we can swap them around. In other words, there are 2 different combinations in which the oldest boy can sit next to the youngest boy. So we multiply that then by 2 factorial, because 2 of them can still be independently assorted. And so there's 6 factorial times 2 factorial different ways in which we can arrange these 2 boys. And if you put that into your calculator, that's going to be 1,440 different combinations. So now let's think about the second bit, which is if the oldest does not sit next to the youngest. Well, surely either the oldest is sitting next to the youngest or he isn't. So we can see that these 2 are complementary events, which means that if we add up the total number of outcomes of both of these complementary events, that must add up to the total number of outcomes we can have. And we can see that if we're arranging 7 boys differently, there are 7 factorial. There are 7 factorial different ways in which we can arrange them. And that actually comes out to be 5,040. So there are 5,040 total ways in which we can arrange these boys. In 1,440 of them, the oldest is sitting next to the youngest, which means in the remainder, the oldest must not be sitting next to the youngest. So the total different number of ways in which they can be seated if the oldest is not. So if that's in our part 2, that comes out to 5,040 minus 1,440, and so the total number of ways in which they can sit if they must not sit next to one another is going to come out to 3,600.